Welcome and hello. This is a video exercise using the HEC-RAS controller titled Depth versus Velocity Relationship. In this exercise, we're going to use the HEC-RAS controller to get the velocity distribution of a cross-section and use that data to compute the depth versus the velocity for a given cross-section and a given flow rate. So let's go ahead and get started. What I have on the screen here is my HEC-RAS. I just opened it up, so I need to start from the beginning by File and creating a new project. So I'm going to navigate to where I want to save this project and project and HEC-RAS directory. Okay, cool. I'm just going to call this project. So click OK. That'll create a project.prj file. I'm going to say yes to accept US customary units, which I can change later if I want. All right, we're going to use some real world data here. We're going to use the Arkansas River, and that begins by going to RAS Mapper. So typically I use the geometric data editor, like GIS tools RAS Mapper. All right, so here we go. I'm going to start by going up to project and set projection. Now I don't have a projection file yet, so I'm going to go to this spatialreference.org webpage to download a projection file. And you kind of have to know where on planet Earth you're going to be working so that you can download and use the correct projection file. This exercise is going to be at a location in Colorado. So based on this UTM map, we are right here in zone 13 north. So if you go to spatialreference.org, that's this webpage here. I'll leave a link in the description. Then scroll down here. I'm going to use an EPSG reference and then just paste in or type in UTM 13N is what I'm going to use. Okay, so we have a few options here. I'm going to use this last one here, EPSG 32613, WGS 84, UTM zone 13 north. So click that and then click on the .prj file. That will download the projection file here at your browser's default download location. So for me, it's right here on the desktop. I'm going to open up my project directory here. So all I have right now is the project file, which is kind of ironic. They have the exact same file extension, but I'm going to be explicit with the file name here and rename this projection to what you see here, projection EPSG 32613 UTM zone 13 and .prj. So there's no confusion as to what that file is. In fact, what I'm going to do is create a new directory and just call it, how about RAS mapper. Therefore, it could be somewhat sequestered from the rest of the HEC-RAS project files. All right, that looks good. Next, I'm going to download the elevation map. So the last tab in the browser I have open here is to a USGS elevation map downloader page. I'll leave a link to this one in the description as well. We are going to scroll in and zoom on southern Colorado. Here is Pueblo. Here is the Arkansas River. So this general area is what I'm looking for. So let's go ahead and scroll down and check on elevation products. And then let's go with the 1/3 arcsecond current. And that looks good. GeoTIFF is the format. So I'm going to click on search products and then just wait for a moment. Boom, here is a panel. So if I zoom out and then hover over that, so this is the pile of elevation data in a GeoTIFF geo-referenced format that I'm going to download. So click this download link right here, and that download has started. If you're curious about more details on this GeoTIFF link, you can click on the metadata link, and that will open up a new tab and tell you things like the datums that are used, the fact that the elevation data is in metric. So, okay, hold on. I think I clicked the wrong link here. Oh, this is the one I want, info/metadata. There we go. If you click on here, it tells you some more information like all elevation values are in meters. So we're going to have to make that conversion when we import it into RAS Mapper. Okay, so here is my TIFF file. It downloaded. I'm also going to put that in the same directory as my projection file. Okay, I have my TIFF file in the project directory where I want it. Let's go back to RAS Mapper now, and we want to load the projection file first. So that is in our RAS Mapper data directory, or at least that's where I put it, and apply and OK. Now down here in terrains, I'm going to go right click, create a new RAS terrain, and then click on the plus symbol here. And here is my TIFF file. So it's queued up for loading. One more thing I need to do here is convert meters to feet. And I think that's good. So I'll click on create. And then this process usually takes about a minute. Okay, so for me, that was about 2 minutes. No problem. Click on close. Boom, here is our terrain. So the color bank kind of gives you an idea of the higher terrain and then the lower terrain. Right here is our Arkansas River flowing in the eastward direction. I'm going to go ahead and scroll in a little bit so we can create our geometry and then add our geometry elements. So right here is as good as any, in my opinion. So let's go ahead and get started. I'm going to go right click on geometry, create new geometry. We'll call it base. And then now I'm going to, yeah, the layer association is correct. So we have that terrain file right there. That's good. So it should be georeferenced later when we open it up in the geometric data editor. On base, let's go ahead and edit the geometry. And let's start with rivers. So I'll click on rivers and then let's zoom in a little bit. I'm just going to kind of guesstimate the center of this river. It's a rather wide river, which actually might be a little bit more forgiving when it comes to some of the data input here. I don't have bathymetry data, so we're just going to use the data that we have right here and double click. River 1, reach 1, close. I like to call it River A, reach 1, and then OK. Next, let's add in some bank lines. So I'll edit the bank lines now and then just single left click to start adding a bank line. This is going to be the right bank line here. As you're sketching, you can also do a right click to sort of recenter. I think it's one of the quicker and easier ways to pan, and double click. And then we want to also add a bank line on the left side. So we'll just go click, 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 right click. Okay, so that's good. And then let's add a few cross sections. So let's see, I'll put one cross section down here at the downstream end of my reach that I sketched. And then how about another cross section here, which is kind of halfway, and then a third cross section sort of at the upstream end of this particular reach. All right, so that's all we need to do there. I'm going to click on stop and say yes to save the edits. So that's all the work we need to do here in HEC and RAS Mapper. So I'm going to save that and then close. Let's open that up in the geometric data editor. I'm going to go edit geometric data and then file. We need to open up that geometry, which is called base. Click OK. Boom, here is that geometry. One thing I like to do to be able to zoom in and zoom out is to go view and then set the schematic plot extents. And then just change these numbers to left and bottom to be lower, top and right to be higher, and then zoom in again. So I'll change that 5 to a 4, that 5 to a 6. Let's see the top, so 4 to a 5, and then that 4 to a 3, and then OK. Okay, so now I have to zoom in, but it now gives me the ability to kind of pan it around and put it where I want on the display, because I like to kind of keep that right up here. If I wanted to bring in that background image, I can just by going to plot terrain. So that's sometimes nice to see, but personally, I'm just going to leave that out of the display for now. Let's take a look at the cross-section data. So here is the cross-section data. Which one is this? This is the upstream most cross-section. And then we have a number of station elevation points. I'm going to click on this is the bottom most cross-section, and then this is the middle. So we have, 1, 2, and 3. As far as node IDs, I'm pretty sure the upstream most node is node ID 1, node ID 2, and node ID 3. So what we're going to be doing at this step is determining which of these 3 cross-sections we actually want to be using for our HEC-RAS controller code and determining the velocity versus depth relationship for. Also, I need to put in my Manning's n values. So let's just do an approximation of that right now. Let's toggle this off, horizontal variation in n. So yes, and I'm just going to use something generic like 0.055 and 0.035. Okay, 0.055, and then apply data. So let's do that for all 3 of the cross sections. Okay, I guess I have to do this manually each time. That's lame. And apply data, and one more. Yep, okay, so options, and okay, so that's done. Also worth checking is the profile, just to make sure we're going downstream, and we are, so check, good sanity check. In fact, at this point, this reminds me what I want to do is determine an approximate slope here, because I'm going to need to set a downstream boundary condition for my steady flow analysis. So let's take a look at these 2 downstream cross sections, which is this one and this one. So we know the run is, we'll just say 8,000 feet. And then the elevation change is going to drop from, what are we, 4423. I'm just approximating here. and then this Thalweg is 4374. So we'll say maybe 50 feet of drop divided by 8,000 feet of run. I've got 0.00625. So that's actually something we need to do right now. I think we got everything we need for the geometry. Oh yeah, we need to decide which cross section to use. So this one looks pretty clean to me. This one doesn't look too bad. Definitely a steeper slope here on the right embankment. And then this one looks a little wonky. I'm going to leave that alone. Let's go with this middle cross section right here. So that would be associated with node ID 2. We could write a script to confirm that, but for now, I'm just going to assume that it's node ID 2. File, save the geometry. Next, let's go to Edit, Steady Flow Data, and then let's click on that downstream boundary condition, normal depth. What did I say? 0.00625. So click OK. Oh, looks good. Okay. Now let's add a few different flow profiles. How about 3? Let's start off with maybe 20,000 CFS, 50,000 CFS, and 100,000 CFS. Then let's see what that looks like when we run them. It may be too much, it may be too little. This is just a wide range for us to determine which flow rate would be best for our analysis. Save flow data. I'll call that base as well. Okay, we can close that now. Now I'm going to run the steady flow. So we need to go run steady flow analysis. I'm going to create a plan first. So save plan. I'm just going to be generic and call this our base case, base, and compute. So let's give this a second. 3 seconds. Close. Now let's take a look at our cross-section data. So go up to the view menu and then cross-section. Okay, so it looks like we have the water surface elevation is way down here. Look at that. So I'm not sure which profile we're looking at here. Options, profiles. So that was the 20,000 CFS flow. Let's add them all. So select all. Okay. Wow. Okay, so there's a huge conveyance capacity in the Arkansas River, apparently. This right here is 100,000 CFS, TF3 that I have selected, which I propose we use for our profile. So our profile ID is going to be 3, and our node ID is going to be 2. I'm sort of thinking ahead to the HEC RAS controller code. So if you hear me mumbling about that, then there's a reason for it. One thing I want to do is also demonstrate how to obtain this velocity distribution chart. First of all, you need to be running a steady flow simulation. And then something else to do is open up your cross-section results, which is what we're looking at. Then you want to go to options and velocity distribution, and then make sure you have this checkbox checked on. So if I had it checked off, which is the default setting, and you click OK, then you're just going to get kind of the generic light blue coloring, unless you happen to change the symbology, but you're not going to see the actual velocity color ramp in your legend the way we had it when we went up to options, velocity distribution, and then check that checkbox on. Now this radio button here for maximum range per plot, that's sort of letting HEC RAS automatically determine what is the maximum, minimum, and step. But if you wanted to manually set the minimum, maximum, and step values for the velocity, you can do that here. I'm going to just let HEC RAS do that part and click OK. All right, so what it's showing me here is I have different colors for 2 feet per second, 3 feet per second, 4 feet per second, all the way to 8 feet per second. I think that'll be good. And if we wanted to control how many different slices there are, so right now I'm only seeing 3 slices. There's a little yellow sliver right here, there's a green and a blue. The blue is clearly the highest velocity, that's 7.31 feet per second. The green right here, that is 5.67 feet per second, and then the yellow is probably just 1 foot per second. I had to zoom in a little bit further. 2.03 feet per second. All right, so what we're going to be doing is taking those velocities and then comparing them with the depth, which I'm going to hold down control and then just kind of measure an average depth for each slice. It's 3.33 feet. Over here, where it's a little bit deeper and the velocity is a little bit higher, that's 5.51 feet. So I want a more discretization in my cross section. So the way to control that is that you come over here to the geometric data editor, bottom left corner, H tab params. And I am only caring about this middle cross section, and I'm only caring about this main channel column. So instead of 5 equally spaced or equal width slices, in my main channel, I want to change that to something higher, like 30. We'll see what happens there. So click OK. And then the cross-section data editor, let's see. I think I need to refresh this. Okay, let me just close it, and then I'll go to the view cross-section, and then let's zoom in. Okay, I still have the same three here. In fact, let me just toggle off the other profiles. So profile ID 1 and 2 can go away. Okay, so that's good. Let's rerun the simulation, and then I think we should have more slices in this particular cross-section view for more colorful list of gradients. Oh yeah, it looks like our velocities increased as well. I think I was looking at the 20,000 CFS data before. This right here is the 100,000 CFS data. So save that in case I need to, and then let's run the steady flow simulation. Okay, that's done. So let's go to View, Cross-Section Data. Now let's zoom in here. Very nice. So now you can see more slices within our main channel, which includes the lower velocities right here, the greens, which is like 2 and 4 feet per second. And then over here we have deeper slices, but also higher velocities, like looks like 10, 12 feet per second. It's time to head over to Excel and write some code to utilize the HEC-RAS controller to get all this data for us. So what I'm going to do is open up a Excel file, and what you're seeing is what I have already set up. I'm going to have a row for each slice. So these are going to be numbered 1, 2, 3, 4, and so on. And then I'm going to return some data such as the left cross-section station for the slice, the right cross-section station for the slice, the flow area for the slice, and the velocity for the slice. Now, as you'll find out, subroutine that we're going to be calling is called output underscore vel dist. It also returns things like the flow percentage, the wetted perimeter, hydraulic depth, and a few things that we're just not going to need in this particular exercise. But it will return these 4 values, and then depth will be calculated, and we're going to plot the depth versus the velocity. And we will have more than 4 slices. It looks like there was closer to 10 or 20 different slices. So we're going to have about 10 or 20 different rows in this table, and we're going to have a plot to take a look at the end of things. Go ahead and click on your Developer tab up here in Excel, and then in the ribbon, click on Visual Basic. Okay. If you haven't already, double click on Sheet 1 or whichever sheet that you have your table set up for. And then what I'm going to do is go up to Tools, References. I need to add the HEC-RAS controller reference, which currently is not added. So if you have HEC-RAS installed on your Windows machine, you should see a HEC River Analysis System, which is right here for me. I'll click the checkbox and click OK. Next, what I'm going to do is just paste in my script here and then explain it. So we're going to be running this subroutine that I wrote called Open Profile Table. And well, it sort of, that's not a good name for it. So I'll just call it vel dist get data. It doesn't really matter what it's called because it's not being called by anything. So this is kind of like my main function, and I'll save that. First thing first is create our HEC-RAS object. That is from the HEC-RAS controller class. And then I'm going to be opening up our project file just by calling this create controller. It should really be called create controller and open project. The creation is really right here, but we're going to be opening up that project. So whichever path it is to your project file, go ahead and update that if you're going to be using my code. After that, we're going to be creating the parameters required for this particular procedure. The procedure is right down here. It's a subroutine called output underscore vel dist. We'll take a look at that in a moment. All of these parameters are required, but the 5 that contain data that are not returned or assigned within the subroutine are right here. River ID 1, reach ID 1, node ID. Now I need to change this to 2 because in my prep I was using the 3rd cross section because it looked best, but this is going to be the 2nd cross section. And then UPDN, that's not used for cross sections, so we'll just assign it 0. And then profile ID, that is going to be our 3rd profile ID. So we have 3 profiles in our steady flow file. So that coincides with 100,000 CFS. All right, as far as all the other parameters here, what you're seeing is the slice count. That's the number of slices that are going to be returned. And then we have a bunch of arrays, which are basically the same data we're looking for. Here's the left stations, the right stations. There's flow percentage. We're not going to use that. Here's the area, so we will want that. Wetted perimeter, don't need it. Flows, don't need it. Hydraulic depths. don't need it, but velocities, we need that one as well. So here is the call to that subroutine. Again, all of this data right here will be populated within the subroutine. And then at the very end, what we're doing is going to print some of that data to our worksheet. So the left station and right station will be in columns 3 and 4. The area will be in column 5 and the velocity in column 8. So taking a look at that worksheet as I have it set up here, we're going to be printing starting in row 4, going downward. There's a row integer variable that's incremented for each loop. And then here are the variables that we're going to be printing out. Depth, of course, we'll have to manually calculate once all the other data is in place. Okay, so let's see if that works. This is always the exciting part. Let me scroll up to the top and then click on Save. I'll pull this off to the side so as it's running, we can see it populate. And then without further ado, run the subroutine. Okay. Oh, that's right. So it also opened and closed the HEC RAS. So I need to open up RAS again. But here we go. We have 17 different slices. And then the left station and right station is good. And if we take the difference, it'll tell us what is the actual width. So 5322 minus 5211 would be about 110, 111 feet. So that should be the same width for all of these slices. And just doing a spot check, yeah, that looks about right. The area of flow seems to be increasing. Looks like we hit a maximum right around here, slices 12, 13, and 14. And then as we approach that right bank, the area decreases. That makes sense. And it looks like the velocity is also similar, like the higher the area, higher velocity. Let's go ahead and calculate this depth now. So it's going to be the area divided by the width of the slice. So it's sort of an average depth for that slice. It's not exact, but it's close enough for what we're doing here. So I'm going to go area and then divided by, open parentheses, right station minus left station, close parentheses, and boom. So the far left slice is only 0.296 feet on average. And then we should get some deeper slices here. So it looks like we're going as deep as 9.7. Yep, 9.5, 9.7, and then it starts getting less deep over here. So very cool. This is successful in my opinion. The last step is to plot this data. If you want to take a visual look at it, insert and then plot. I'm just going to do a quick XY scatter plot here. So on the horizontal axis, this looks like the depth in feet, and then the vertical axis is the velocity in feet per second. So you can see we have somewhat of a linear relationship between depth and velocity here because the axes are also linear. And this looks like, for the most part, a straight line. I think that would fit pretty well. And that's it for this exercise. What we did was use the HEC RAS controller to extract this data that's associated with a single cross section in our steady flow profile at a single flow rate. And then with the area slice width, we were able to calculate the depth and also come up with an approximate relationship between the depth and the velocity.